Okay, hi everyone. So thank you very much for joining our special edition of the Wits Geotalks. So today we have thank our two speakers who are very special guests. They both have decades of experience working in the diamond industry. So they're going to do a joint talk. So first up, we have Dr. Bruce Kjaersgaard. He works for the Geological Survey of Canada. And he is based in Ottawa, in Ontario. And then the second half of the talk is going to be by George Reed. He's vice president at Star Diamond Corporation, also in Canada. Star Diamonds are busy evaluating the Fort Corn diamond deposit in Saskatchewan. And so between the two of them, they're going to be sharing lots of insights in how to find diamond deposits and how to evaluate diamond deposits and why determining the grade for a diamond deposit is so very different to determining the grade for other deposits. And so with that, I'm going to hand over to Bruce. Bruce, if you can just turn your video on so we can see you and we can see your presentation. Perfect. We can see you. Perfect. We can't hear you. Can you just say hi?
Okay, all set?
All set. Okay, so I'm going to mute our...
All right, good afternoon. So as Karen introduced George and myself, this will be a joint talk on the economic evaluation of diamond deposits. And I'm going to be specifically looking at the geological aspects and the importance of the geology in trying to do the evaluation. So the first thing of interest is when we think about commodity price. Simple question might be, what's the price of gold or numerous other commodities? And what's the price of diamond? And so anyone who has a smartphone can go onto the London Metal Exchange and get the price of copper, aluminum, or zinc. And you can find out the price of gold fairly easily. And then can you find the price of diamonds? And the answer to that is no. And the geology is very important to understanding diamonds. So we have different types of primary diamond deposits. So these include kimberlites, carbonate-rich olivine lamproites, which have previously been termed micaceous kimberlites, group 2 kimberlites, and orangites. And these are now recognized to be a variety of olivine lamproites. And of course, we have olivine lamproites. So these are the kimberlite, corals, and olivine lamproites of the three main sources of diamonds from magmatic deposits. And you also get other rocks, such as metamorphic rocks and meteorite, meteor impact, that also are diamond bearing. And the secondary deposits are plasters and paleoplasters from the primary deposits. So I'm going to mostly concentrate this talk on kimberlites. And out of these three main magmatic source rocks, kimberlites, corals, and olivine lamproites, they all are similar in that they all contain olivine, and significantly they contain large olivines. And so you have olivine macrocrysts, which is just means large olivine grains, and these can be xenocrysts from the mantle or high pressure phenocrysts. So we just have some examples here: kimberlites, corals, and olivine lamproites, and you can see all the large grains are olivine. It's quite important to separate out different types of kimberlites. So we just have some examples here. So this is a hypabyssal kimberlite. It's an intrusion. We have massive volcaniclastic kimberlite. This is a fragmental rock. These were called tough acidic kimberlite breccias. We have pyroclastic kimberlites, again, fragmental. And all of these pyroclastic and massive and hypabyssal rocks can all be reworked by various processes, such as resedimentation or fluvial or marine reworking. So for diamond evaluation, we need to be able to distinguish different phases, extrusive, intrusive, re-sedimented, and also subphases. And we need to do that so the diamond variability can be assessed. And we know that grade, diamond grade, and the price of diamonds can be very different from phase to phase in a single body. And if you do not recognize these distinct phases in the geology, it compromises your sampling strategy. So given that kimberlites and these other rocks are from magmas, we need to know something about igneous petrology, and we can use basic tactics, petrography, mineralogy, mineral chemistry, geochemistry, and basic tactics from volcanology and sedimentology, which has a lot to do with determining the size of the class and the types of the class. And basically all of these constitute the explorationist toolkit. The key aspect is that you need to measure the grain size of the crystals and the components. So you have to measure, no guessing. This is very important. And basically what you can do when you're looking at a kimberlite, when you're logging core, is you can use a modified componentry analysis from the volcanology literature. So they look at melt, lithic, and crystals. So for kimberlites, we're going to look at lapilli, ash, and ground mass. If it's an intrusive rock, then we have all different kinds of crustal and mantle xenoliths. Those are lithics and all sorts of crystals. So why do we want to do this quantitative componentry? Well, that's fairly simple. The specific gravity of olivine and diamond are not identical, but they're similar. And we can use olivine to give us some ideas about the size distribution of olivine. So both olivine and diamond have quite a range in sizes. And it's been shown in studies by Field et al. And Harvey et al. That there is certainly a relationship between the size of olivine and diamond. So this is probably the best reason to do quantitative componentry. It can also help sort out subphases or even phases that look very similar but are not. So if we look at the terminology of volcanic vents or volcanic pipes or diatremes, fairly simple. We have a vent with a volcanic edifice, pyroclastic rocks in the volcanic edifice, resedimented rocks in the crater, more pyroclastic rocks, which become weakly stratified, typically massive rocks, and these form from bedded pyroclastic rocks and then a variety of hypoabyssal intrusions. So we basically have pyroclastic rocks, massive volcaniclastic rocks, coherent or hypoabyssal rocks. And this is quite key to understanding the geology. So some examples. And the one thing with kimberlites is they range from quite small to very large kimberlites. And so what we say here, here's our two smaller economically viable kimberlite pipes, Internationalea in Russia and Diavik A154 North. And here we can see the internal geology. So note that there's a couple different hypoabyssal intrusions. There's 4 pyroclastic phases and 2 resedimented phases. This kimberlite has a surface area of about 75 meters in diameter. It's very small, and that's also true for international. So these are very small kimberlites. They're also extremely high grade. We get on to some larger pipes. This is a twin pipe from Russia, Udaknea. And again, note that there are 5 phases of kimberlite in this. Juaneng, triple pipe from Botswana. Again, just note that the variation in the geology from pipe to pipe to pipe and within the pipe. And an example of olivine lamproite from Australia, Argyle, 7 phases, multiple feeder vents, and certainly different phases within discrete domains at Argyle. And this green area and some of these yellow late intrusions are exceptionally high grade. And some examples from Canada, Fort Elacorn, George Reed will be talking more about those, and some additional 3D solids models from Diavik and Lac de Gras, and some examples from Lac de Gras, Acadie, and just geometry, overall 3D geometry, and then some internal morphology of some of these Acadie pipes. Again, so very complex. If we go back to South Africa, to Kimberley, this is a historical photo on the right here, and there's kimberlite in this former open pit. And one might ask, well, why is there still kimberlite in Kimberley, in the big hole? And it's fairly simple. Why are you going to mine something that's not economic? So this phase of kimberlite was known to be low grade and also have very poor quality brown diamonds. And Percy Wagner suggested that it was identical to the kimberlite and the diamonds in the St. Augustine mine, and suggested there was a fissure that connected the two. So you can have the kimberlite, which is economic, but not all parts of it are economic. And this is well shown from work from Roger Clement's thesis in the Kimberley area. So this is a geological plan and section for the Detroit's pan. And we can see that, first of all, there's a whole bunch of different phases. There's hypabyssal kimberlites and fragmental kimberlites at the same structural level. And there are certainly grade variations between these phases. And also here in this phase here, there's differing diamond grades. So an interesting question that you're going to ask as a geologist is, how do you get an intrusion and a fragmental rock sitting side by side at the same structural level? And you ask the question, well, what volcanic processes are happening? What's the emplacement mechanism? And when you think about forming a pipe, or when you think about volcanic fragmentation, you have to look at either magmatic fluids, or you have to introduce external groundwater. So these are called fuel coolant interactions, phreatomagmatism. And if you have adjacent fragmental, non-fragmental rocks, that means the kimberlite magma in those two rocks had to have very different initial volatile contents, or they were similar and you had to introduce water from an external source. So the emplacement mechanism is important because it affects the pipe geometry and the size of the pipe. So this is potential ore tonnage, and the style of volcanism or intrusion can affect the diamond grade, either by enhancing the grade or by diluting the grade. So we'll now have a look at some of these processes a bit more. So in kimberlite intrusions, we have flowage segregation. So if you have any material, so if you have water in a pipe or air in a pipe, there's always more friction. So you get a faster flow velocity in the middle, and you can carry larger grains. And so you can certainly see this on hand sample scale and within a dike, where you've got coarser and larger olivines here, and you've got finer olivines here, and something similar here. So these are both examples of flowage segregation on a small scale, and some very careful sampling work done by Clement as part of his PhD. This is DB3 intrusion. And just look, this is much higher grade over here than this over here. And so you can look at this and say, well, is this an example of flowage segregation. Another interesting aspect that we see in kimberlite intrusions in dikes. So this is a single dike from Somerset Island, and typical on echelon form, and you have bridges between the segments, and the bridges are constrictions, and you can get filter pressing. So we start out over here. We have normal looking kimberlite, large olivine macrocrysts. We're losing in the next segment the really large crystals. And then when you get over here, it's basically a carbonate rich kimberlite. So nice euhedral magmatic calcite grains here. So we've lost all the big grains. This is basically like putting a magma through a sieve. Okay, so another example here, Snap Lake. This is a very shallow dike, and there's segments to the dike, and you get horsetails, and it splits up and it bifurcates. So this is problematic for mining. And the other issue, of course, is there's structural problems. If you have a 3 meter wide sill or a 3 meter wide dike, usually you have about 1.5 meters on either side of incompetent rock, and that means a lot of rock bolting, which is expensive. And you can get all sorts of weird things happening with these at these bridges in these systems. If we go to some pyroclastic processes, so this is a star kimberlite, and we have a feeder vent here, and we have a tooth ring in the early Jolly Fu phase. This is a later phase where you have the crater actually filled in from an adjacent kimberlite. The important thing here, though, is when you think about it, you have volcanic eruption. So coarser material close to the vent, finer material farther away. And based on evaluation work, inside the tooth ring, so basically from here to here, you have higher diamond grades and larger stone size distribution. And when you get outside the tooth ring, you get lower grades and basically finer diamonds. In contrast, when you go up to Lac de Gras and you look at a kimberlite like this, you can see it's layered, and then you have to explain how did this happen. So the only real viable mechanism is, instead of having a tooth ring, you have a more significant volcanic edifice, a tephra cone, and you have to slump that material back in. And when you look at these phases and subphases in here, this basically all consists of resedimented volcaniclastic kimberlite. And these are talus fan or grain flow deposits. So we need to know what kind of kimberlite it is: pyroclastic, volcaniclastic, massive volcaniclastic, resedimented volcaniclastic, hypabyssal. And these kimberlites, they're all kimberlites, but they're forming by different processes, and the processes affect diamond grade, stone size and distribution, and pipe size and geometry. So all of those factors should be influencing your sampling strategy for evaluation. Now, as geologists, unfortunately, we're sitting down at the bottom of this upside down triangle. And so core logging, which is super, super important in the whole process, is often undervalued. And yet, the further you go along in the evaluation process, you're spending more and more and more money and time, and you're all doing it based on core logging. And this is basically what I call an unstable situation. And in Canada, we've had a number of mine closures, and each mine closure has been due to multiple factors, but one commonality is a suboptimum understanding of the geology. So I'd have to emphasize that the core logging part and understanding the geology is extremely important to carry out a viable, robust evaluation process. Okay, so George is going to get into the next section and discuss diamond rough prices, grade, the ore value, size of deposits a bit. And just remember that diamond does not have a fixed price, and that's completely different from just about any other ore deposit that you might want to think about, be it gold or base metals or platinum group metals. Okay, and that's it for me. Thanks very much, and I'm going to turn it over to George now.
George, you're going to come through?
Yep, I'm just sharing my screen now. We should be, are we good to go yet?
Yes, if you can just fix the display settings because it's not on full screen.
How do we do that?
Yeah, so display settings at the top.
Okay,
And then do the swap presenter and slide.
is that better?
We can only see you. We can't see your slides.
That's no good. Okay, we'll have to, hang on a minute, sorry, I must do this, go back to. How about now?
Not yet.
That's real quick.
We had it earlier. It's weird that it's not
Yeah.
working now.
You can just see me now.
I can just see you. Yeah.
And then
Can you start from step one again? So go back to share screen.
okay, and we'll go here and we'll say share.
Here we go.
And we'll open up here.
And then just go full screen. Yeah.
Yes.
And now go to display settings at the top and then just click swap presenter and slide.
Are we good?
Now we're
Thank
good. Okay, take it away, George. Thank you.
Thank you very much. Is this bar on the slide? Can you see that? No. You can see the slide in full. Good afternoon, everybody, and I'm very pleased to be with you. It's a pleasure to be able to present this talk. I'm very happy to see some eminent names from the past among the external viewers. Anyway, without further ado, we've got a lot of concepts to look at the beginning, and then I'll hopefully excite you with some actual project pictures and let you know exactly how we do this and give you a feeling for the extreme effort that goes into a project like this. So without further ado, let's dive in, and we've got to work out these numbers: tons, how much kimberlite is present; grade, how many diamonds are present in that kimberlite; and then most importantly, we've got to recover at least a 2,000 carat parcel of commercial goods so that we can determine a reasonably accurate average run-of-mine dollar per carat price for those diamonds. And in amongst these sections, you can see there are many subsections. Kimberlite size, the internal structure comes from pattern core drilling. We'll look at that in detail. Geological continuity, as you saw with that very tabular kimberlite, the mushroom shape of the Fort-Alacorn. As we go out into the more proximal parts of the kimberlite, we need to look at this geological continuity. We need to do very detailed core logging. And as Bruce impressed upon us, we need to actually measure core metrics and determine clast sizes, abundance of certain clasts, particularly the mantle component, which will give us a proxy for diamond in the kimberlite. We need to accurately measure kimberlite density all the way along so that we have a good idea on variations in density, so that from our drill core, we can convert volume to tonnage. We need to also look at the rock strength and do the geotechnical measurements as we go, so that ultimately when we have to build a pit, we have those numbers in place. So the grade is usually expressed, particularly in Africa, in carats per 100 tons. Many bodies in Canada, it's carats per ton, because there are more than 100 carats per 100 tons. We must remember that a carat is a 0.2 of a gram. We use initially, when we recover a kimberlite, we would look at micro diamonds, very small diamonds all the way down to perhaps 50 microns, but usually stopping at about 150 microns and going up into the macro diamond range at 0.85 millimeters. And then, but we must remember, when we mine diamonds, commercial goods are anything that sits on a number 1 DTC, that's the Diamond Trading Company screen, which is 1.09 millimeters, round screen, if I remember correctly. So we've got to look at the dollar per carat price, and the dollar per carat price is always in US dollars. We need to do some sort of bulk sampling, and so there are a variety of methods. If the kimberlite is at surface, we can do pitting and trenching directly from surface, but that only tells us what's right at the very top. We need to do large diameter drilling so that we can recover reasonably large numbers of kimberlites, particularly macro goods, so that we can determine grade variation across the kimberlite. Then, in order to do, if the kimberlite, such as in the Fort-Alacorn, is remote from surface, we need to do underground bulk sampling. Underground bulk sampling is obviously very expensive. We have to sink a shaft. We'll talk about that as we go. And then more recently, Rio Tinto has very successfully shown the use of a trench cutter, which is a very large volume drill that enabled us to get down 250 meters below surface and recover a very large parcel of diamonds. We have to ensure in our plant, when we are preparing the evaluation results for these bulk samples, that there is a very good liberation of small diamonds, particularly if there are high value stones among the smalls. We need to avoid diamond breakage. That is a message that can't be said strong enough. Obviously, the large diamonds are exponentially more valuable than the little ones, and we have to recover them whole and ensure that they are not stolen during evaluation. So with collation of this information, we need to move from initially building a geological model, as Bruce showed in his previous slides. Then we need to add a block model that shows the variation within that, and create a mine or an open pit that would then be able to recover that, and we determine a mineral resource with inferred, indicated, and measured mineral resources with increasing rigor and statistical constraint on those. From that, we can go to a preliminary economic assessment where we add the costs of exploitation to the project, perhaps a pre-feasibility study, and then ultimately a feasibility study where we have a plus minus 15% view on what it will actually cost to build and run a mine. So there are other variations we need to look at. As Bruce has already mentioned, there is diamond grade and diamond value or diamond price, as shown on this chart. And note that it has logarithmic scales, so there is enormous variation in the grade. These are all mines that have been economically, from which diamonds have been economically recovered. Notice that up in the top left, we have Argyle with the yellow dot, which has very high grade, but very low value. And fortunately for Argyle, it produced some of the most remarkable pink and red diamonds that sold for, some of them, over $1 million a carat. Jwaneng, which is up here, it has high grade, high value, and high tonnage. It is probably the world's most valuable mine out of almost all commodities. It is a real money maker for Botswana and De Beers. At the other end of the scale, we have down here very low grade, between 1 and 3 carats per 100 tons. We have Letseng in the highlands of the mountains in Lesotho with very low grade, but very high value, and dollar per carat values that range between $2,000 and $3,000 per carat, average price for the production. The other variant on diamonds that we need to understand is natural diamond populations that are brought to the surface by kimberlites have log normal size distributions of their components. So what does that mean? It means that there are infinitely more little ones than big ones. And the economic drivers of the project are always the big ones. The big diamonds are exponentially more valuable than the little ones, but all of them will have some value and have portions of the market that desire specific types of goods, as we refer to them. On the chart, the size frequency diagram, logarithmic scales with carat size increasing to the top of the chart, and critical stone size increasing across the chart, and the proportion of carats to the top of the chart, very low proportion at the top and high proportion at the bottom. Lots of little stones at the bottom of those diagrams and very few at the top of them. These are 3 unusual kimberlites, namely Letseng in Lesotho, with these very big high-value stones. You see on the table on the left-hand side, 3 carats per 100, or 1.75 carats per 100 tons, and $2,100 per carat. And going up to the largest stone on that chart was the Lesotho Promise, which was 603 carats. That was done in a paper by Debbie Bone and others. We can see the blue line on for Karowe mine in Botswana, operated by Lucara. And again, a very coarse size frequency distribution. And this kimberlite has produced 3 of the most valuable stones and the largest stones in recent history, running up to $1,700 a carat, and the Constellation, which sold for an enormous value at 834 carats. So there is this size frequency distribution that we can take into account, and certainly we see that the star kimberlite in red lies in between those, and we anticipate seeing some very large diamonds recovered from star in future production. If we look at the project site, this is in the Canadian Prairies, some 3 hours drive north of Saskatoon, about 60 kilometers as the crow flies east of the city of Prince Albert, which has about 35,000 people. The Saskatchewan River in the background. It is 20 kilometers off paved highway and at 20 kilometers off a power grid. So it's very accessible. There were always rumors in the past about people having pizza delivered to site from the local pizza supplier, which suggests that it is very different to what you would see for the mines in the north, which are at the end of an ice road and only accessible by air in the winter. You can see extensive work. Those pads were all for large diameter drill sites. There was a processing plant. That plant has been upgraded since then. Certainly a very active site. Bruce has already shown this slide, but just to remind you that we have in the greens in the lower part of the diagram, those are the kimberlites that we're targeting, but remembering that there is some 135 meters of overburden on the star kimberlite, 100 meters or so on the Orion South kimberlite. And so everything has to be sampled remotely. Hence, it was so important ultimately to get a bulk sample from this project. We needed to sink a shaft and do an underground development. So in order to understand the size and the internal structure of this body, we carried out a pattern drilling program. This was a very intensive program. This was done in 2005 and 6, and we had lots of money. The market was flush with money, and we had a very extensive program. These were petroleum rigs drilling PQ core 75 millimeters they were modified for drilling kimberlite. It was a very, very speedy process. We could drill a hole down to 300 meters below surface in essentially 3 days and move on to the next site. The holes were spaced about 150 meters apart on a staggered grid to give us a very good distribution in this kimberlite, which is very, very large in aerial extent. Bruce mentioned earlier the Diavik kimberlite and International, which are only about 1 hectare in size. The size of Star, where this drill is placed, is 350 hectares surface area. And so you can see we drilled 320 large diameter drill holes in, or core holes in Star, and 186 in Orion South. We then got onto our core logging. Obviously, this picture is taken a while ago. You can see my beard has still got some color in it, and it's not just white. But certainly there was a big team of geologists that did the core logging, and the core logging was done to a very specific standard. All of the core was then audited by a committee, and any unusual interfaces in the geological model were then actually revisited in the core and resolved by the committee. So very, very rigorous. We also did whole rock geochemistry. Whole rock geochemistry was instrumental in distinguishing the kimberlite phases within Star apart from the visual observation. Core is all important, as Bruce emphasized in his top-heavy triangle. And as a consequence of that, we were very, very sure to archive this core so that we could return to the core to check anything very easily. And all of the core from both the Star kimberlite and the Orion South kimberlite are housed in this warehouse, and it's very accessible. Every box is accessible. They all sit on metal rails and they can be pulled out. We have a scissor lift that gives us access to this warehouse, laid out on the floor, and then we have tables so we don't have to bend down too hard to see the core. It has been very successful. So I mentioned that we did an underground bulk sample. Certainly this was a complicated process because the overlying sediments were some 20 meters of unconsolidated sand, and then the rest down to about 100 meters below surface was glacial till, and then Colorado mudstone after that. And so we actually had to freeze the overburden with pipes drilled down to 130 meters and then blast through that a concrete lined shaft with classical mining gear. You can see here a whole bunch of geologists and a miner packed into a kibble going underground to do some work. And then all of the ore came up and down that shaft in the kibble, air supply on the right-hand side. And we can see we get underground. It's classical drifting, 8 by 8 foot drift. Some of them were bigger. Everything had to be netted and bolted. And as you can see in the Star Underground, it was a very successful operation. It was done in 3 phases of 25,000 tons. We took out a total of 75,000 tons, from which we recovered over 84,000 stones, plus 1 millimeter in size, and some almost 11,000 carats, an overall grade of about 14 carats per 100 tons. But lo and behold, the largest stone was 49.5 carats, and that was already speaking to the very coarse size frequency distribution that we have in the Star Kimberlite. We then moved over to Orion South. We replicated the similar underground bulk sampling program on Orion South. We had only removed some 23,000 tons of material, giving us 15,000 stones and some just over 2,000 carats. The going was more difficult. There were some very ash-filled areas which were unstable. They required a lot of geotechnical work, lots of rock bolts, netting and shotcrete. While Mark and I were standing there looking at the rocks, there were rocks falling down at the end of that drift, but we were under the netted and bolted part, so we were quite safe. Certainly, and then we were unfortunately impacted at Orion South by the world financial crisis of August 2008, and the work on Orion South, both underground core drilling and large diameter drilling, had to be curtailed in the first quarter of 2009. But again, most important to see that the largest stone recovered from that underground program was just under 46 carats. So again, a coarse size frequency distribution. So the underground development was in a fairly limited part of the kimberlite. In Star, we had about 3 kilometers of underground tunnel in underground lateral development, but in Orion South, we had less than that. So we needed to do grade determination across the kimberlite and in the vertical through the kimberlite up and down. And so we used these Bauer large diameter drills that could drill a 1.4 meter diameter hole down to at least 300 meters. There's the drill bit, which was, unbeknown to us at the time, a rather aggressive approach. You see the big vent on the top of that bit that sucks in the slurry and pumps it to surface over a screen that extracts the kimberlite, and then the slurry is then recycled. The drills were successful, but because of the aggressive nature of these drill bits, there was unfortunately diamond breakage, and so the size frequency distribution did not exactly match the underground bulk sampling, which we believe is fully representative of the size frequency distribution. And we had to then, in our mineral resource calculation, we had to apply a coefficient to the large diameter drilling results, which was done with very rigorous statistical parameters. Obviously, in Saskatchewan, you get a very cold winter down to minus 40 degrees centigrade. And I'm very pleased to say that we successfully drilled through some very cold days with these Bauer rigs. We used a lot of steam. We used a lot of natural gas and propane to heat the system. But the machines were all filled with Arctic oils, and this picture was taken on a sort of relatively mild minus 27 degree day where everybody was at work. Then later in the life of the project, we have done a joint venture with Rio Tinto, and Rio Tinto wanted to do additional large sampling, bulk sampling of the Star Kimberlite to show the grade and prove to themselves the grade and the size frequency distribution. And they managed to persuade Bauer to build these trench cutter rigs that are normally built for cutoff walls down to about 50 meters, but this rig could go down to 250 meters below surface, recover kimberlite from an enormous rectangular hole that is 3.2 by 1.5 meters in size, sample to 250 meters below surface, and every 10 meters of advance produces 100 theoretical tons of kimberlite. So an enormous volume of material is recovered. The kimberlite is then recovered from the slurry and stored in these bulk bags, which we can see in the drilling program. We recovered 6,848 bulk bags of kimberlite that await processing through the plant, which in this picture you can see was still being built. Lo and behold, this plant was finally finished. It was a Rolls-Royce of a plant with a very good high-tech systems in it, a high-pressure grinding roll to ensure the liberation of the small diamonds and recover the bottom end of the size frequency curve very well. It used dense media separation, but with a very small size fraction going through the DMS cyclone, and only 1 to 6 millimeters. It made the DMS very efficient in recovering the small diamonds. And then for the large diamonds, it used a TOMRA XRT, X-ray transmission sorter, which identifies the diamond by its composition. So normally in the plant, diamonds are recovered by density, 3.52 grams per cubic centimeter, through a dense media separator. In some plants, they use grease. Diamonds are oleophilic or hydrophobic, and they stick to grease. And then latterly, XRT sorting has come into its own and is very successful, particularly at the recovery of large diamonds before they are broken. As an example, on the Karowe kimberlite in Botswana, under the leadership of their VPX John Armstrong, they have, I think, 7 times increased the top cutoff. They have a mega diamond recovery plant, which looks at ore before it goes into the crushing circuit. And that's where diamonds such as the Lesedi Larona and the Suelo, which are both over 1,000 carats, have been recovered. So now we've collected a huge amount of information, and we have to build geological models in 3 dimensions of these kimberlites, and then from that build up grade models, grade block models, where we show the grade variation across these multiple phases of kimberlite, all of which have been samples. That then is collated into this mineral resource estimate, and we can see a plan view. Notice the scale, which has a 500-meter grid, so it's quite a few kilometers from edge to edge, left to right across the screen. The underground is the spider web here in the middle in black. That's 3 kilometers of underground development on Star. The gray diamonds are core holes. The yellow squares are large diameter drill holes. There was a ravine here, which we weren't allowed to enter from an environmental point of view. Otherwise, there would have been more large diameter drilling in this ravine. But fortunately, across the ravine, or underlying the ravine, there is very good geological continuity that we could prove from the core drilling, which then assisted in the resource development. So by this stage, we have our mineral resource defined. The blue line is the pit boundary. The green line is where the inferred kimberlite lies within that line, and the red line going back to the inner part of the eruptive vent, which Bruce originally alluded to, is where the indicated a much higher statistical resolution of the diamond grades. And all of that material obviously is recovered. We then prepared a preliminary economic assessment where we could then cost the recovery of this the diamonds from this kimberlite, develop the whole system. We showed that 470 million tons at a rate of 45,000 tons per day could go through the plant at an average carat weight, a carat grade of 14 carats per 100 tons, and a total recovery of 66 million carats over a 34-year mine life. And then we give the economic parameters of the kimberlite, which is a net present value at a discount rate of borrowing the money to build the mine of 7%, $3.3 billion NPV, and a 22% IRR in the base case. When we add post-tax and royalties to that, the NPV is still a very strong number with a $20 billion and a 19% IRR. Obviously, the pre-production capital cost of building such a big mine is 1.4 billion, not a small number. But once you get going on a diamond mine, it makes money very quickly, and that 1.4 billion is paid back in 3.4 years of production. And remember, you have a 34-year life of mine for the simultaneous mining of Star and Orion South. The removal of the overburden was very costly with truck and shovel, and we looked at other methods of removing the overburden, from dredging to bucket wheel excavators. Certainly bucket wheel excavators, which were used on coal mines in what was formerly East Germany, were the obvious choice, with unit costs of about 40 Canadian cents per ton. And so it was very, very advantageous to go with bucket wheel excavators. We worked very closely with Tackraft to do that, and obviously the use of XRT sorters in the processing plant to ensure the recovery of the big diamonds without breaking them. The general arrangement for the layout of such a mine, Orion South pit going first because of its shallower overburden, followed by the Star pit. The plant is in purple, centralized processing plant for both. The material would be moved by conveyor to the plant, and everything would be as much equipment as possible would be powered with electricity as opposed to diesel. The bucket wheel excavators would be electrically powered and moving the waste by conveyor onto the overburden waste pile. Coarse kimberlite containment facilities and a fine processed kimberlite containment facility on the east side of the project, power line coming in from the southeast, and as I said, only 20 k's off the Saskatchewan power grid. If we then look at the carat production, I'm running out of time here. We have the blue carat production is from Orion South, moving over to the red dominated carat production from Star, and you can see the Star diamonds are generally more valuable, but we get into valuable diamonds earlier on Orion South, hence putting Orion South first. We then look at a cash flow model, and certainly it goes negative, and then by 3.4 years we start making money, and lo and behold, a huge amount of money is generated in the life of the project. Just to look at some sensitivities, the project is very sensitive to the diamond price and grade, which you see in the green line. It's also very sensitive to the exchange rate, remembering that the diamonds are sold in US dollars, and the payment of the project is in, or the operating costs of the project are in Canadian dollars. And so that sort of exchange rate is very beneficial. And certainly when you are in a place like South Africa, which has a huge exchange rate difference between the South African rand and the US dollar, that can be very advantageous. I'm essentially at the end. We have a vast amount of technical and financial information that needs to be rigorously collected. You can't say that strongly enough, and integrated to fully estimate the economic value of a diamond mine. Diamond deposits have a wide diversity of variables, grade, price, tons, that can collectively make an economic mine. Experienced technical and financial managers are required, particularly those who embrace innovation. We don't want to just say, we've always done it like this, so let's continue doing it like this. We will just continue to break the big diamonds. Let's get away from that. And then never lose sight of the fact that simultaneous to preparing all of this information about the technical and financial aspects of the project. We need to look at the social and environmental impacts and get the approval from the local communities and the stakeholders to build a mine. Thank you very much.
Thank you very much to George and to Bruce for giving us such a thorough overview of the complexities of diamond mining and all the different factors that have to be considered when evaluating a diamond deposit and deciding whether you can proceed with mining or not. And so are there any questions from anyone here in the room or online? You can just type your message into the chat. Could you come to the microphone, please?
Hello, George and Bruce. Thank you so much. Just a question. Did you start mining underground just to start to recover some cost? And then you're planning to do open pit? Or I missed the connection between the underground operation and
the underground development was just as a bulk sampling exercise. And in future, there will probably not be underground mining. The future mine would be open pit down to 350 meters below surface.
Okay, thank you.
I just asked to raise their hand.
So maybe you can raise your hand if you have an online question, and then we can bring you forward and then you can ask a question.
I have actually another question because you have overburden of 300 meters.
No, 100 meters, 135 meters on Star and about 100 meters on Orion South. So 100 meters of overburden, and the pit would go down to 350 meters below surface. So there's a lot of kimberlite, 470 million tons of kimberlite between the two bodies that can be recovered.
Oh, thank you very much. Any other questions from anybody over here? Yes. Oh yeah, Linda has more questions, so she's gonna just keep going.
Yeah, I was just thinking now which kind of social engagement you have or the community. I'm just thinking of the situation in South Africa, and how the mining company are actually helping community for infrastructure, since the services are not so well developed by the government. I'm wondering how is the situation in Canada about social license to mine?
There is obviously it's very important to have an interaction with the local communities prior to building the mine and prior to proceeding with building the mine, and actually it's integral in the development of the environmental impact statement and the acceptance of the impact statement by both the provincial and the federal government. And in Canada, we have to ensure that both of those regulatory authorities are satisfied, particularly in the case of the STAR project, because the federal authorities come into play when water is involved. So in our build up to hopefully building this mine, we have developed what we call the Diamond Development Advisory Committee, and there are people from every community and indigenous group that are represented on that community. And the project then on a regular, at least a quarterly basis, those communities are then informed of the project and can voice their concerns. And ultimately, once a decision is made to proceed with a mine, then impact benefit agreements with communities would be negotiated and put in place. And there would certainly be great opportunities for local communities to participate in the project and provide services, and it can be extremely advantageous for both employment and making money in those communities.
Thank you. Thank you very much. Thank you.
Okay, we have another question here from in the room.
Thank you both for a really good talk. This is perhaps more directed to Bruce. You obviously spoke about different facies variations affecting grade of kimberlite, but I'm wondering if larger scale craton-wide factors can affect diamond grade, and if there are any much bigger, like geotectonic factors that affect diamond grade.
That's an interesting question. Yeah, so whether like well, we know like Botswana and South Africa are producing lots of large diamonds, but why are there no large diamonds routinely being recovered out of Canada, for example? And yeah, maybe either Bruce or George could answer that.
That's a great question. I think my first comment would be, seem to get lots of large stones out of Southern Africa, Cap Vel. And then you go to Slave Craton, or you go to Yakutia, and we don't get the big stones, but we get fantastic diamond grades with good stone quality. So if you look at the Diavik pipes, they're like 4 or 5 carats per 100 tons, or 500, sorry, 5 carats per ton or 500 carats. And then if you go to Russia, similarly, you know, Internationalea, it's basically 10 carats per ton or 1,000 carats per 100 ton, just phenomenal. So there's definitely cratonic controls on the, you could say, the size distribution of the diamonds in the mantle that's being sampled, and also the number of diamonds. So there's certainly very craton specific hallmarks of the different cratons.
Yeah.
We just don't know what's causing it.
Well, I can make a comment on it, and Andy Moore has obviously raised the subject of clipper diamonds. While I won't speak specifically to clipper because we don't have sufficient information on diamond inclusions, but certainly in Star, Orion South, and very much in Orion North, which is further to the north, there are very high, unusually high proportions of type 2A diamonds in the population. So for Star, we have about 26% of type 2A, and for a similar size range in Letseng, that percentage is 29%. In Orion North, that percent goes up to it, and it's a poorly constrained sample based on large diameter drilling results, but that percentage goes up to 50%. So certainly once you get into the specials, which are diamonds above 10.8 carats, certainly the type 2A diamonds, which are nitrogen-free diamonds, potentially formed at great depth, have unusual characteristics. They can be the most perfect gin and tonic white, or they can be slightly brown. They can be changed with high pressure, high temperature work, and there can also be pink diamonds among them. But the type 2As are very much present at Star and Orion South, and we also know there is a proportion at Orion North. I am unaware of the exact proportions of type 2As in the northern kimberlites, Diavik and Ekati. There are a few big stones, but they're rare by comparison.
Yeah, and I
Does that answer the question?
That's another factor, right? Is there could be large diamonds in these other mines or these other cratons. However, whether there are sufficient amount of these diamonds to actually justify trying to recover them and implementing a large diamond recovery unit into your plant to justify that cost. That's another factor. So other cratons and localities may have these larger goods, but whether it's actually economically viable to try recover them is a different factor.
Alan Jones asked a question about a geophysical response relating to economics. I'm not a geophysicist, and it's a difficult question to answer, but there was a relationship that I can recall from past work with De Beers, where some of the targets that were of lower significance from a geophysical anomaly point of view, prove to be the better kimberlites. But there would be a very long discussion on that. I think a guy like Gavin Self might be able to give you an answer on that.
I think I would add in there that based on just a lot of different geophysics done on kimberlites in Canada, and also the Russians were on about this quite a long time ago. And of course, I think a lot of people just sort of poo-pooed it, but certainly the low mag signature kimberlites seem to be a lot more interesting economically. And I think one of the Russian ideas was if you have a very magnetic kimberlite, which means you have a lot of magnetite, and this all has to do with oxidation. And if you have a low magnetic kimberlite, it's perhaps more reducing and it's better for diamond preservation. But other than that, I don't think there's any geophysics silver bullets.
I think I'd agree with that.
The one geophysical success in the Fort-Hiller Corn was time domain EM was used some almost 20 years ago, and a fellow from Australia who is Croatian, I think, I can't remember his name, did the interpretation, and certainly that was the best definition of the actual size and kimberlite boundaries in the Fort-Hiller Corn. It was very, very successful in delineating the bodies accurately with geophysics.
Okay, well, if there are no other questions, then I'd just like to thank our speakers again. So thank you very much, George. Thank you very much, Bruce. Thank you for your time, taking time out of your busy schedule to give us this very interesting presentation. So thank you very much.
Thank you very much.
Thank you.
Okay, so I'm going to end this.